honored that you asked me to come and speak today. Well, so everyone's pumped full of coffee, and we're a little bit over time, so since I'm pumped with coffee too, I'm going to go as fast as I can. Because I'm giving the first LIGO talk of the day, I thought, well, I could show some pretty pictures of LIGO, and I could show, the GW 5914 waveform and all of that. Or I could show something that people care about, which is the latest O2 observing status. And this is all public, so there are no secrets in here. So O2 began at the end of November of this past year. We decided to extend O2 through August of this year. The average duty cycle is high now. It's sitting at about 60 to 70%. This is an improvement over the beginning of the run when we had much poorer duty cycle. We've collected a total of 48 days of coincident Hanford Livingston data so far. There was a scheduled break that occurred at the end of December, the beginning of January, we've achieved an average range of about 70 megaparsecs for binary neutron stars, 300 megaparsecs for 10 on 10 solar mass binary black hole mergers, and 700 megaparsecs for heavier stellar mass binary black hole mergers. We've identified 6 triggers so far with our online analysis. Those are the triggers that have satisfied a false alarm rate threshold of less than once per month, and that's the threshold to share triggers with our observing partners. The analysis is ongoing, so more about that soon, hopefully. The latest news is that we are right now in the middle of a brief commissioning break that started on May 8th and will last for about another 2 weeks. The main goal is to clean and eliminate an absorbing spot on one of the Hanford input test masses. And both Hanford and Livingston have been partly vented and will have to be pumped back down at the end of this break. So Advanced Virgo has been locked and has been locked repeatedly over the past year. Virgo is working on commissioning and getting the noise down. So this is the latest public Virgo noise curve. The blue curve here is the measured sum of all of these different noise sources. And the goal, the target sensitivity, is all the way down here. Excuse me. That's right. Okay. Right now, this noise curve gives you a binary neutron star range of only about a megaparsec. So there's a long way to go, but Virgo's making good progress.
Well, they recently increased it by a factor of 4 in like 1 day, so they just have to do that about twice more.
There you go.
That's just the way it works.
So that's it on the sort of instrumentation side. On the data analysis side, a lot of us are starting to get very excited about transitioning to 3 detector operations. Virgo is expected to be a part of O3. That's the next observing run, but we are feverishly preparing for the possibility that Virgo will contribute some data toward the end of O2, which would be tremendously exciting. So on the Virgo side, that means that their data quality and detector characterization teams are ramping up and starting to look at and try to characterize glitches, for example. In both LIGO and Virgo, we are adapting our data analysis pipelines to handle 3 detectors. So in S6, the last run of initial LIGO, we had 3 detectors, and our pipelines could deal with that. But we, because we went offline for several years then to upgrade our detectors, everyone rewrote all their codes because people had to get PhD theses, and that's what you do. And so now we have much more sensitive and much more powerful pipelines that are optimized for 2 detectors. And so we have to go back and fix that. But there are some genuine and interesting challenges to deal with 3 detectors when you do sky localization and when you include coherence of phases and amplitudes across a network of detectors. And so that's something that's being done. So this is taking up this is, when we're not looking at O2 data, this is what we're working on. And so the reason why we're all very excited about the possibility of Virgo coming online with some sensitivity before the end of O2 is that these awful, hundreds or 1,000 square degrees localizations that we've gotten with our 2 detector network will shrink dramatically, even if Virgo comes online with a tiny fraction of the sensitivity that LIGO has at the same time, say a quarter of the sensitivity. So we go from several hundred square degrees to, in some exceptional cases, barely 100 square degrees. So the most important thing about having 3 detectors is that we need to have a global network of gravitational wave observatories in order to do coincidence. So we require detections of multiple detectors to claim that we've seen something that might be astrophysical, and we also need multiple detectors to do sky localization. So we have the 2 LIGO sites, of course. Soon we'll have Virgo back, and we'll also have Kagra and LIGO India by the time that LSST comes online. Here's how you do sky localization. You can either start from the strain time series that you get from the detectors. So you have n detectors and m time samples, or you can do match filtering and get a point estimate of the amplitude, time, and phase on arrival in each detector. There are a bunch of nuisance variables that you have to get rid of in some way by, for instance, marginalizing them away. Those include the masses and the spins. And there are extrinsic nuisance variables, the absolute arrival time of the signal at some fiducial point in space, the distance, the inclination, and the polarization angle and orbital phase of binary. And once you get rid of all these nuisance variables, you're left with the direction of the source. So here's a back of the envelope derivation of the timing uncertainty, which gives you a sort of order of magnitude estimate of the angular resolution of a network of gravitational wave detectors. So this is a noise curve. I guess this is the second noise curve that I showed in this presentation, but I should explain the axes. On the horizontal axis, you have the gravitational wave frequency, and on the vertical axis, you have the amplitude spectral density of the instrumental noise. So what you do is you take the amplitude spectral density of the noise, and you take the amplitude spectral density of the signal. I'm assuming that we're talking about compact binary sources here, so to a 0th order approximation, the power spectral density is just f to the minus 7/3, and you do a weighted integral of these two things, and you get a sort of effective bandwidth that contains different moments of frequency weighted by the ratio of these two curves. The timing uncertainty is just 1 over the signal to noise times that effective angular frequency. So at advanced LIGO's final design sensitivity at an SNR of 10, you get a timing uncertainty of about 0.14 milliseconds for binary neutron stars, or about 0.27 milliseconds for neutron star black holes. And I'm already at 10 minutes. I've just barely started. 9 minutes? Oh. Okay. So there's more to it than that. So we would never distribute sky maps that are based solely on timing, because we have these expensive, multi-million-dollar detectors, and we wouldn't, we want to use every single piece of information that we have to give the best localization possible. So it's better to think of the network of gravitational wave detectors as a phased array, sort of like an array of radio telescopes. Each detector gives you not just a time of arrival, but also a phase and an amplitude. So even if you're just doing triangulation, and when I say triangulation, I don't mean using times, I mean using times, phases, and amplitudes. Even with 2 detectors, you can do much better than just a sort of annulus on the sky. The other thing that helps you, in addition to the phase coherence, is that our detectors have a directional sensitivity that we call an antenna pattern, and the directionality is different for the two gravitational wave sensitive polarizations that we can sense, the so-called plus pattern and thank you, the cross pattern. And so this also helps you cut down on the localization area and also gives you a very, very coarse estimate of the distance of the source. So the nuts and bolts are that we have basically 4 different flavors of how we do localization. We start with 2 different types of assumptions about the nature of the signal. We either consider unmodeled burst signals or modeled or template-based compact binary coalescence searches. And then for both unmodeled bursts and compact binaries, we have both a rapid localization that takes a few minutes and a refined parameter estimation that takes a lot longer. So we have, I guess I won't go through the details here because they're just different names of pipelines and loopers. But okay, so in 2014, before a few years before advanced LIGO started, Mansi Kasawal, Samaya Nissanka, and I were putting out papers that were trying to show that we could in fact localize sources with 2 networks of gravitational wave detectors. This was because at this time, the sort of party line that people would give about LIGO localizations is that, oh, you can't do anything with just 2 detectors. You'll get these annuli in the sky, and no one's going to bother following that up. So the purposes of these papers were to sort of challenge those assumptions and show that if you use phases and amplitudes, that you can do much better than you could using than you might assume if you were just using the sort of back of the envelope calculation that I described earlier. And Mansi Kasawal and Samaya Nissanka all further tried to argue that, or argued that kilonova follow-up would be challenging but possible with ground-based optical surveys like ZTF, dark energy survey, LSST, and so on and so forth, even if you have only 2 detectors. So this was a message that, I think we intended to be optimistic about the early years of advanced LIGO, 01 and 02, but I'm afraid that it has created an unrealistically pessimistic expectation about what the more distant future, the sort of LSST era, should be like. So this is a figure and a table from the LIGO Observing Scenarios document, which is a part of the Living Reviews in Relativity series. So we've been talking about these 2 columns here, 2015, 2016, and 2016 and 2017. What's relevant for LSST is 2019 and beyond. So these numbers, again, just come from that back of the envelope timing calculation. And we estimate that we will be able to localize, well, in 2022, when we have Hanford, Livingston, Virgo, and LIGO India, we should be able to localize 20% or more of our binary neutron star sources to better than 5 square degrees, and half or more of our sources to better than 20 square degrees. This is some software that I've been working on with a colleague of mine at Goddard, Tito Del Canton, and it just sort of automates the process of making these sorts of tables. But it will be, and the purpose of this is to make it so that I never have to actually make another one of these talks. I can just show people my software and someone else can give this talk. No, just kidding. But so this is this is a map on the sky of localizations of binary neutron star signals at an SNR of 12. Here's this color map indicates the distance to which you can detect the sources. So this is the direction-dependent horizon distance, and these ticks indicate the sensitivity of the detectors. So as you add LIGO India, that's what the I stands for. The sensitivity becomes across the sky, sorry, the horizon distance across the sky becomes much more uniform. And you get far fewer of these long, thin arcs. Then if you add COGRA, so you have 5 detectors, those awful arcs basically go away, and you have an almost uniform horizon distance across the sky. So the message here is that, by the time LSST comes online, we shouldn't be thinking of hundreds or 1,000 square degrees. We should be at least for sources that we detect when all 5 detectors are online. It'll be more typical to localize sources to tens of square degrees or a few square degrees in the best cases. So it could, we should be thinking of maybe 1 to a few LSST fields, not tens. So I'm going to draw it to a close and just say, there are a few other games that we can play. We can, since we can localize, we can also infer distances. We can play games where we combine our gravitational wave localization with a catalog of nearby galaxies or a map of galaxy clusters, and so we can prioritize follow-up to target nearby galaxies. Xinyu Chen and Daniel Holtz have been thinking about sort of taking this to the extreme of sort of looking at the very, very best localized sources and trying to figure out if we could, if there's one or a few golden events that we might see that we might be able to directly identify the host galaxy just because the error region is small enough. That's the end of my slides, and I have a few questions that we can use to start discussion, or you can ask your own questions. Thank you. Go ahead.
Yeah, I want to ask a little more about what we've done so far in LIGO. We're using 2 detectors that are aligned, counter-aligned.
Mm-hmm.
And great, you guys were able to do better than an annulus. That is all fine. But then when we add a 3rd detector, we're no longer aligned, so polarization matters. And I am not so clear in what you've said that once the data is analyzed, the waveforms are done and so forth, I understand what we can do. But in terms of determining where it comes from in a fast trigger, can you really get rid of or ignore or take care of the polarization? Or know enough to take care of the polarization?
Yes.
Are we fast you can?
Yeah, that's what, I mean, all 4 of these pipelines do that.
Probabilistically, I mean, it's in a way. I mean, it's using a prior to do that, but it's a good assumption. I mean, for the distributional sources.
The things that we can't do in low latency right now are deal with, we don't deal with calibration uncertainty. So our full parameter.
It's being done.
It's being, I'm sorry, that's right.
There is an online calibration which is actually performing pretty well now.
Well, there's online calibration, but what I'm saying is we don't marginalize over the uncertainty in that calibration in low latency. So when we send out, our initial sky map, our refined sky map from our parameter estimation will usually be coarser, and that's because we've folded in those systematic errors. That should become less of an issue in the LSST era because there are a number of tricks that we can play to do our calibration better online, so that there is less of a difference between the first version and the final version of the calibration. Did I answer your question?
I have to read what you've got.
Okay, I
don't buy it totally. I mean, you have different detectors with different sensitivity and different orientations. It's very different.
Discussion.
It's very different than the problem that we have now. And I understand you can start with a prior, but I have a hard time seeing how you can determine any unknown polarization configuration quickly and accurately when all the amplitudes and sensitivities are different and unknown. But I guess if you've done it, I'll read it. But I don't.
Yeah, all the pipelines, even the wrapped ones do that. Yeah.
So let me suggest we transition to the discussion. Leo will be a part of it, so we'll have a chance to talk to you more. If you know that you're on the first panel, please come forward.